Let's analyze and solve the valid parentheses coding problem. We are given a string S, and we are being told that the string only contains brackets. And we have to return true if the string is valid, otherwise we have to return false. And we are also given a rules that we have to use to decide whether the string is valid or not. The first rule says that every opening bracket must be closed by the same type of bracket. So to give an example of that rule, the valid string would be, let's say we have opening square bracket and we have a closing square bracket. So this is the valid string. The invalid string, according to that rule, would be we have a opening square bracket, but we have a curly brace closing bracket. So this is invalid. The next rule says that all opened brackets must be eventually closed. So for that rule, a valid string would be, again, something like open bracket, close bracket, close bracket. So all open brackets are closed. And the invalid string would be something like open bracket, again, open bracket, close bracket, and there is a missing close bracket for the first square bracket. So this is incorrect. This is invalid. The next rule says that opening brackets must be closed in the correct order. So if we have a string, the valid string would look like, for example, we have square bracket, curly bracket, open paren, and then we close them in proper order, which is close paren, close square brace, close curly brace, and close square bracket. So this is correct string. Incorrect string would be, let's say we have a open square bracket, open curly brace, close square bracket, close curly brace. This is incorrect because the order is not matching. This open curly brace is closed by the square bracket, which is not correct. And the last rule is very simple. It basically says that we cannot have a closing bracket like this before the opening bracket. This is incorrect. With these rules in mind, we have to write a function. Let's call it isValid. The function will receive one argument called s. It's a string. And the function should return true or false, depending whether the provided string is valid or invalid. We are also given a set of constraints regarding the string size. What we can notice is that the string is never empty, so it will have at least one character. And additionally, the string will only contain brackets. There will be no other characters in the string. To solve that problem, we can start from a simple brute force approach. Let's use one of our examples, example 1, which is like this. I am going to write it again. And the simple brute force approach would be to notice that at some point in the valid string, there will be a matching pair of brackets, which we are going to remove from the string. And after removing that pair, there will be again a matching pair of brackets, and this one and this one. So we can remove those. And finally, the last remaining pair will also be matching after removing the previous brackets. So we can now remove those two. And we will end up with an empty string. So the test whether the string is valid will be, we will check whether the remaining string is empty or not empty. In this case, the string is empty, so we say the string was valid. Going for the same approach with the string from example 2, which is invalid, let's test this. So we have curly brace, square brace, paren, square brace, paren, curly brace. So according to the same method, we would search, is there a matching pair of brackets? So we will check, is there a matching pair of two parens? There is none. Then we will check if there is a matching pair of two square brackets. There is none, because there is no sequence square bracket in that string. And we will finally check, is there a matching pair of curly braces? And again, it's not. So at this point, we will end our algorithm and we would check whether the remaining string is empty, and it's not because we didn't remove anything. And this would be indicator that the string is invalid. And to give you one more example, let's write some more complicated strings. So open square bracket, maybe something like this. Close, again open, close, and close square bracket. So to test the same algorithm on that string, which is a little bit more complicated, we would find the matching curly braces. We would remove those two. Then we would search again for a curly brace, but there is no curly brace. So we would search for, let's say, square brackets. We would remove those two. There is no more matching square brackets. We would search for the open and close parent, and then we would find this pair, which we would remove, and this pair, these two, they will be removed. And we would repeat the process from the beginning. So again, we would search from curly braces, parents, and square brackets, and we would find, oh, there is a pair of square brackets which we can remove. So we would remove this one, and then the process would end because we just removed everything and we ended up with the empty string. That means this is a valid string. And there is basically an idea for brute force algorithm for this problem. The complexity of this algorithm is O of n squared. And the space complexity is O of 1 because we don't use any additional memory. And why it is O of n squared? So if we have a string of size n, we have to search that string for the parent, and then each time we basically remove two characters, but we still have to search this string n divided by 2 times, assuming the string is valid. So there will be at most n divided by 2 searches, and for each search we have to do removal, which is also O of n. So we do n times 2 times n, and we ignore constants. So that's how we end up with the quadratic time complexity. And that's pretty much the brute force solution. The brute force solution works, but we can do better. And let me write down the example 1 string again. So it was like this. And what we can notice by looking at the string is that there is a rule that if we are processing that string and we find a closing bracket, that bracket must match the last bracket that was opened. Like in this case, we have a closing parenthesis. So the rule would be that the last open has to be open parenthesis. And it is in our case. So in this case, we could say that the closing parenthesis is fine. We would move to the next character, which is closing bracket, square bracket. And we would see that the last open now is the open square bracket. They also match. Then we would move to the next character, and this is the closing curly brace. And the last open remaining is the open curly brace. That means the whole string is valid. Everything matches. And if we can see this, we can also see that we could use a FIFO data structure like stack to store the opened brackets, so we know which was the last that was open. So let's do it with a stack. So let me remove this, and we will process it again, this time using a stack. So here is our stack, and we will start from the first character. This is the open curly brace. So we would put that open curly brace on our stack, and we would move to the next one. This is again open bracket, open square bracket. We can put this on our stack, and we move to the next one, which is again open parentheses, it goes to our stack, and the top of the stack is now here. And we move to the next character, and we finally found the first closing bracket, which is specifically closing parentheses. And now we do the test. We see if the one at the top of the stack matches our current character. If it doesn't match or the stack is empty, that means that string is invalid. But if they match, we can remove the top of the stack, which is this, and move the top of the stack one level down. And we can move in our string to the next character we are testing. And this is the closing square bracket. It again matches the top of the stack. So we can remove this one from the top of the stack and move the top of the stack to the previous character. And we move in our string. We now are at the closing curly brace, and it matches what we have in our stack. So we can again empty the stack, and we reached at the end of our string. So, and everything matched, and that way we can conclude that the string was valid. And this works with one additional catch. Let's add one opening character at the end of the string. So let's say open parentheses. If we had one extra character, we would move to the next one. It's open parentheses, so we would put this at the top of the stack, and then we would reach the end of our string, and everything matched, except that this is incorrect. We have opening parentheses, but we are missing a closing parentheses. So at the end of our algorithm, what we also have to do is to check if at the end the stack is empty. And if it's not empty, like in this case, that would indicate that our string is invalid. And that's the idea for this solution. The complexity of this solution is O of n, because we just have to process the string once. The n is the length of the string. And the space complexity is O of n. It is O of n divided by 2 for the valid string, pretty much, but we are ignoring constants, so it is O of n. And these are the complexity formulas for our solution. Let's write code for our two solutions, starting from the brute force solution. So we will define an array of string pairs first, so const standard array, and it will be array of strings, so standard string. And we have 3 types of pairs, so it will have size 3, and let's call it bracket pairs. Values in that array will be open parentheses, close parentheses, open square bracket, close square bracket, and the last one is with the braces, open and close. And now we will need a flag because we will be looping through that string and searching for those pairs. So let's have a flag, a Boolean flag, call it changed, and we will initialize with true just to enter the loop. And we will need a position when to store the place where we found the pair. So it's gonna be standard string, and string has a type called size type, and this will be our position. And then we will start our loop. So while changed, that's why we initialize it to true above to enter the loop for the first time. And then inside that loop, we will be searching for all the pairs. So for const auto reference to our brackets in bracket pairs. And for each of those, we will be searching if these are in our string. So while we have to store the position. So while pos equals our s.find, and we are looking for the brackets. So if we find the brackets, and in C++, there is a special constant that indicates that we didn't find anything. It's called standard string npos. So if this is different than npos, that means we found something. We found the brackets, and so we have to set the flag change equals true. And I forgot, we have to set it after entering the while loop to false. So changed equals false. This way, if we never find it here in line 24, that means we can end the loop. And after that, we have to erase the string. So s.erase, and we have to erase starting from the position we found the brackets at, and we have to erase those two characters, open and close bracket. And as we mentioned earlier, once we exit that loop, that while loop, that means that we cannot find any of those three brackets in our string anymore. So we have to check if that string is empty. If the string is empty, that means we were able to remove all matching pairs and the string was valid. Otherwise, if the string is not empty, that means the string was invalid. So we basically return whether the string is empty. And that's pretty much our brute force algorithm. Let's try to build it. And I have around 20 tests written for this problem. So I am going to run those tests. And all the tests have passed. So our brute force algorithm works. Let's write the code for our optimal stack-based solution. So we need to include stack. And for this solution, I will write a small function, small utility function. So an idea for this function is that provided with the open parentheses as an argument, it will return a matching parentheses as a result. So let's write it as a const expression to enable compiler performance optimizations. And the function will return a character, and let's call it matching close bracket, long descriptive name. And the input will be character C, and the body of the function is going to be very simple. So just a switch statement, and based on the input argument. And we are going to check all the three open brackets. So let's start from the open parentheses, case open parentheses. And if this is the case, we will return the matching close parentheses. And I will copy this 3 times for different brackets. So square bracket, close square bracket, and the curly braces. If we are called with something which is not a open bracket, we will return null character. So we will return null, and this is convenient because in the condition, the null character will evaluate to false. So now let's move to our isValid function. And first we need to define the stack. So standard stack. And it's going to be stack of characters. And let's name it just stack, st. And then we have to process all the characters in our input string. So for const char c in our string, we will be doing the following. So first, we have to check if this is the open or close bracket. For this, we can use our our function, because this function will return them. If this is an open bracket, we will get a matching closed bracket. Otherwise, we will get 0, which evaluates to false. So we can do if matching bracket of our C. So if we have a matching bracket, that means that C is the open bracket. So let me write a comment here. C must be one of the open brackets. And in this case, we can just add this to our stack. So st.push C. And otherwise, if we get here, that means that C is one of the closing brackets. It cannot be anything else because we are guaranteed that the string itself will only contain brackets. So if it's a closing bracket, then we have to see if the top of the stack matches our current closing bracket. For that, the stack cannot be empty. So the first check we have to do is to make sure the stack is not empty. If it's empty, that means we can immediately return false because our string would be invalid. So if st is empty, then we just return false. Otherwise, we have to check if our current closed bracket matches the one the one on the stack. And for that, we can do the following. If we call our function, so on the stack, there is some open bracket. So if we call our function with the top of the stack, and on the top of the stack, there is some opening bracket, and this function will return the matching closing bracket for the one which is on the stack. And it has to be, if it's different than the current bracket we are considering, so if it's different than C, that means we have a mismatch and we can return false. Otherwise, the bracket matched, so we can remove from the stack, so st.pop. And this will continue until we process all the characters in our string, or if we find that the string is invalid, we will return from within that for loop. But at the end, as we said, we have to also check if after processing all those characters, whether the stack is empty. Stack has to be empty for the string to be valid. So we can basically return st.empty as the result of that function. And that is pretty much the code for our stack-based solution. So let's try to build it. It builds correctly, and let's again try to run our tests. And our tests failed. And our tests failed because I forgot the return. And so let's build it again. And now let's hope the test will pass. And the tests have passed. So with a little trouble, we coded our stack-based optimal solution. Let's make sure our solutions pass all the LeetCode tests. So I am going to start from the brute force. I copy the brute force into the LeetCode environment. Let's see if this works. It works. Let's submit that solution and see if we can pass all the tests. Yes, we can. And our brute force solution works. Let's make sure that our optimal stack-based solution works in LeetCode. So I'm going to paste it into the LeetCode. And let's see if it runs. And it runs, so let's try to submit this. And it has passed all the tests and the performance looks good. That's the end of this solution. The source code is available in the GitHub repo shown on the screen.